Okay, so everyone, this is Andrew. He's a software developer from London with a strong background in mathematics and computer science. While working in industry, he ended up developing a compiler for a domain-specific language for finance and trading, implemented in Haskell. He also likes to read medieval Welsh manuscripts and riding horses. And today he will give you an experience report and a guided tour of the bittrack package. So please welcome Andrew.
Hi there. I'm going to talk about bit vectors and best ways to implement them in Haskell. So bit vector is a simple thing. It's just an array of booleans, and as conventional wisdom tells us, it can be represented as an unboxed vector from package vector of bool. Yeah, where bool is true or false, so true stands for 1 and false stands for 0, for example. And it's a very nice representation, and I think we can finish our talk at this point, unless someone is unhappy with vector of bool as a representation for bit vectors. Let's talk a bit more about compromises which are involved in using vector of bool in its existing implementation. So good parts of vector are that package vector, it provides us with quite faithful vectors, so they allocate a continuous chunk of memory, they allow random access, and they have mutable vectors as well with constant time updates, and we have slicing, so we can slice our vector into sub-vectors in no time because it's just modifying offset and length, and it is not materializing vector altogether. And we have loop fusion framework to save intermediate locations, and we have rich API. But what is bad when we use vector of bool to represent a bit vector is that, first of all, we allocate too much memory, because vector of bool actually allocates a byte for each bit. It allocates word 8 per value. So we just require 8 times more space than theoretically possible if we pack values 8 bits per byte, as it would be expected probably. And another thing is that in vector API, we are obliged to process arrays basically element by element. And in our case, elements are so small that it becomes a disadvantage. Because, for example, if I just want to invert all bits in my vector, I really do not want to do it bit by bit. I know that it's a continuous chunk of memory, and I would like to use some nice vector operation of my CPU, just saying it like, please invert at least 64 bits at once, and better invert like 512 or something like this. But due to limitations of generic vector interface, we cannot do it. So mapping and, for example, zipping of bit vectors is 64 times slower than it could be possible on the same hardware if we would be able to operate on word 64 level, for example. And another alternative to vector package is array package, which is an older one. And it, again, a nice array in imperative programming, continuous memory chunk, random access, mutable counterpart. And the benefit in comparison to vector is that array package stores 64 bits, 64 bools per one word, which is ideal way of storing bits. But negative part is that we are still limited to bit by bit processing. We do not have any slicing capabilities. We basically need to materialize all slices and basically copy them. And there is no loop fusion framework, and API of array package is very much limited. So we have a better memory, but it's not that convenient as vector. One more option is that we can use int sets from containers package to represent bit vectors. The idea is that instead of storing actual vector of zeros and ones, we can just store a set of indices for which correspondent bits are set. And it's the best representation if your bit vectors are sparse, so they have only several non-zero bits. It potentially could store more than 8 values per word, so it's maybe better than vector package, but worse than array package. And what is good is that some set operations like union, intersection, and whatever, they are capable to process basically on word level blockwise. So it can zip 64 bits with another 64 bits in one CPU instruction, basically, in some cases. And of course, containers have very nice, rich API. Bad parts are that our memory representation is no more continuous. There are a lot of pointers. It's not quite cache friendly, and random access and random updates are no more constant time operations. They are log n operations. The fourth alternative to represent bit vectors, and actually it's in some sense better than all three others, is a very simple one. We just say, okay, we need to represent bit vectors, which is just a sequence of zeros and ones of arbitrary length. So let's just use integer. And this approach is implemented in BV package. So again, integer in Haskell is backed by libgmp library usually. So it's continuous memory, random access, it's packed. So we have 64 bits per word, and you are usually capable to process 64 elements at once. So for example, if you have two vectors represented as integer, and you want, for example, to zip them with AND operation, then you can just use AND from bits type class for integer, which will employ libgmp, and it will work very efficiently, returning a new integer. So far, so good. But the devil is that there are no mutable counterpart for integer, obviously. So if you need to update just one bit in your bit vector, you need to reallocate the entire structure. You need to copy your integer, flip that bit, change it, and you pay a lot for updates, for garbage collection, and while we have all these benefits which I listed above, these updates are terrible. It will just you'll just spend all your savings on them. So let's talk about bit vectors without compromises. We would like to have full-fledged vector and mutable vector instances with expected asymptotic complexities. We would like to have bits instance providing us with vectorized blockwise operations like AND, OR, XOR, NOT, and so forth. And we would like to store our data as compact as possible, so no compromises. We would like to use all our memories 64 bits per word, 64. And it seems quite doable. Well, if we need to define a new instance of vector for some data type, we can just define a new type bit, which is a new type over bool, and we define data bitrack, which is a triple of actual payload represented as a byte array. and two ints. So first one says from which point of our byte array actual payload begins, and how long is our bit vector in the second int. This looks all quite simple, and we can easily implement indexing in this structure. So if we want to get a value of ith bit in this bitrack, we need to determine its actual position. So we need to determine in which word it is allocated. So we add I to offset, and we divide it by word size. So I am assuming that word size on our platform is 64. We read corresponding word, and we just test bit, which corresponds to reminder so in this word, and return bit. All nice and good, and it looks like it's quite fast, and it actually is. So we have a way to read values from our vectors. Now we need some way to write values into our mutable bit vector. Again, vector package requires us to define one more data type, which is quite similar to previous one. Again, we have offset and length, and we have an array. This time it's not byte array, but it's mutable byte array. And we can implement mutation of this bit vector writing in quite similar spirit to indexing. Again, we need to learn about actual position in our mutable byte array. We need to find in which word is located our bit, and actually location of our bit inside that word. And all nice and good. We have all functions available from GHC base package. So we just read word, then we either set or clear relevant bit in it, and then write it back. Looks very good. Unfortunately, there is a problem, because what would happen if we use this write function in a concurrent environment where several threads are writing into our vector concurrently? So in this line, we read a word, 64 bits, from our array. Then we computed new value of this word, and then we write it down. But the problem is that, imagine that I asked I run two threads, and first thread is writing one to first bit, and second thread is writing one to the second bit. And if they started at the very same time, then both of them read an empty word at this place. And then one of them is attempting to write a word with only first bit set, and the second thread is attempting to write a word with only the second bit set. One of them will win, but I will end up with a byte array where only one bit is set, while I would expect to have 2 bits, because I run in 2 threads functions which should have set first and second bits as well. So general solution in concurrent environment is to implement to have some atomic compare and swap function, which basically is a primitive to implement synchronization between concurrent threads. So this function takes array and offset in this array, and you also pass expected old value of this array at offset, and you also pass a new value, which you would like to write at this position. And what this primitive should check, it actually checks if actual value in this array is still an expected old value, then write it. Otherwise, do not do nothing, because it seems that that another thread has already spoiled our array. And in this case, we just need to return actual new value and ask our caller to produce new value corresponding to the actual value of this word in array. And this can be used in our case as well, but we end up having basically a self-recursive function go, which will run compare and swap array. And if compare and swap was successful, then we are done. And if it's not, then it will just go for one more round. It doesn't look very much appealing, and usually such recursive functions have pretty slow runtime because of recursive calls. But we can do better. It appears that GHC provides functions which allows us to basically or XOR and AND some memory segment in atomic way. So instead of reading, then modifying, then writing back, we can just employ these primitive atomic functions, saying them, please modify array at position Q with apply or with this word, with a word where only one bit is set. So if we want to write a true bit, then we apply or with a word containing required bit set. And if we need to clear some bit, then we use atomic AND, and we use a word where everything is set except that particular bit. So this gives us a safe, thread-safe version of write function. And thanks to having these primitives, it's not terribly slow. It's like maybe 20% slower than usual approach. Going further, so we have read and we have write, and the next function is modify. And the vector package is happy to provide us with a built-in modify function, which is actually implemented in terms of read and write. So you pass an array, you pass a modifying function, and you pass an offset, and it will modify by the value of at this offset applying this function. What is interesting is that in our case, restricted to bits, yeah, there are not so much functions from bit to bit, which we can use to modify our array. Actually, there are only 4 functions. So first of them is ID. Well, if you intended to modify this ID, then don't modify at all. It's also const true and const false. But if you want to use const true or const false, then you can probably just immediately write true or false. And the only non-trivial option is inversion, is function not. So we are asking to flip some particular bit in our bit vector. And we can implement it just by read and write. We already have read and write, but again, it's completely wrong in concurrent environment, because, for example, if I run 2 flip bits for the same position in vector, I expect that vector will eventually be unchanged because flip and flip is ID. But actually, if they are executed in a concurrent fashion, I may end up with flipping that bit. So again, we are lucky to have this primitive XOR in base package, which provides us with a way to flip bit both fast, so we do not need to read and write as separate operations, and also thread safe. And it's like twice faster than modify function from which is in stock. Defining vector and mutable vector instances requires also defining some blockwise functions like copy, move, set, grow, and all of them need to deal correctly with offsets and length of our vectors, and all of them could be like sub word size and even sub byte size. So it's a bit difficult to write all of them correctly from the very beginning. And actually, so bitrack package was developed like 5 years ago, and its first version was quite buggy in edge cases for copy and grow, for example. And the reason is that it's quite difficult to debug all these cases, especially in mutable environment. And I took over this package a year ago, and when I took over its maintainership, I basically started with writing property tests, because the only good way to check all these pesky, gritty details is write some properties. So I have written about 30 properties for testing unboxed mutable vectors. They test various options of offsets, lengths, sequences of operations, and this is available from Quick Check Classes package, and it's also available for Hedgehog. Again, Hedgehog Classes package. Since then, I employed this set of properties for bitrack and for some other my packages, and it was very useful. I'm quite happy that I have some properties which I can reuse, and I encourage everyone defining their instances for unboxed vectors, especially if it's an untrivial one, to use these property set. So far, we covered our vectors. Now let's go for bits interface. So as I announced before, I would like to have some blockwise map function for my bit vector. So usual map function, which is provided by vector package again, as I told before, it operates element by element, one by one. But actually, if we restrict our vectors to bits only, again, we see that map requires us to provide a function from bit to bit. And again, there are only 4 functions from bit to bit, and the only non-trivial one is not. So if I map my vector with not function, I'm basically computing a complement of my data. So bitrack package defines invertbits function, which operates on blockwise. It reads your vector word by word, so 64 bits at once, and complement these words and write them back. So it gives us 64 faster implementations than map with not. Again, we need to take extra care for unaligned vectors in concurrent environment. And the ultimate speed up comes from using libgmp, because libgmp is usually available in GHC, and it's widely available on most distributions, and GHC use integer GMP. It uses libgmp to back all its integers. And it appears that GMP actually provides an mpn-com routine, which is very fast because it's backed by some ASM code, which uses which inverts like 512 bits in one instruction, and on some machines even more. So it gives us very nice speed up if GMP library is available. And going further, so we can also talk about blockwise zipping. Again, vector
Andrew,
package.
sorry,
Yeah.
sorry to interrupt, but you have a question from Edward Matt. Do you implement the map function as well, or just the invert bits?
I implement this package implements only invert bits, but one can implement map basically by checking which of these with which of these four functions we are dealing with. So one can implement it as well.
Thank you.
And in case of zip, again, there are only 16 functions from bit to bit to bit. And bitrack package implements this function zip, which takes a function from bit to bit to bit. It detects internally which function actually we are dealing with. Is it like conjunction? Is it disjunction? Is it some not and or and not or exclusive or? And it is able to employ the most efficient backend once it has detected what function it is. Again, we can use blockwise operations on Word. Again, it's even more difficult to align two vectors for zipping efficiently because they can have different offsets. And again, we can use libgmp for even better performance because it again has libgmp again implements all these 16 base functions in assembly, and once we dispatch to a correct one, it works very fast. So we need just to detect which of these 16 functions we are dealing with, which can be done just by basically testing it on 4 values, and we are good to dispatch to the correct, to the required GMP routine. There are some additional goodness in bitrack, so there are some implementation of Boolean polynomials, there are conversions from vector of word and from byte string, there are pop count and its reverse. There are operations required to implement succinct data structure backed by some modern CPU instructions and stuff. So to recap, we ended up having a full-fledged vector and m-vector instances with expected asymptotic complexity. The only downside is the constant factor is a bit larger, especially for thread-safe functions, which is quite expected because we need to lock some memory locations. We also have handy bits instance with vectorized operations, so they're usually at least 64 times faster, and if we are fortunate to have libgmp available, it's up to 1000 times faster for some kinds of payload. Again, we are not compromising our memory requirements. We are storing each bit in 1 bit, so it's 8 bit per byte and 64 bit per word. So I guess that's it. I'll upload my talk shortly on GitHub here, and you can find source code of this package here. Thank you very much for attention.